Assalamu alaikum, respected teacher and my dear classmates. I am Sifat Sharif from CSE department, CSE427, section 02. Me and my friends named Enayat Ali and Naimul Hassan Choudhury are presenting our project titled A Comparative Sentiment Analysis on Tweets Using Simple and Complex Models. I briefly introduce the project and then give an overview of our work. First of all, social media has become an important platform where people share their opinions and emotions. Among different platforms, Twitter is widely used because people post short messages called tweets about their events, products, and social issues. Because a large number of tweets are posted every day, manual analysis is not possible. Sentiment analysis helps classify tweets as positive, negative, or neutral, while emotional analysis identifies emotions such as joy, anger, fear, and trust. The main objective of our project is to analyze sentiments and emotions from Twitter data and to compare simple machine learning models with deep learning models to understand which performs better on informal and noisy text. For the overview, we used a public Twitter dataset from Kaggle that contains around 25,000 English tweets labeled with sentiments and emotional categories. Before applying models, we cleaned the data with removing special characters, usernames, and extra spaces, and by converting all text to lowercase. This helped improve the quality of the data. We then applied two types of models. The type, the first type includes traditional machine learning models such as naive Bayes, KNN, and random forest. The second type includes deep learning models like RNN, bidirectional RNN, and LSTM, which can understand word, order, and context. After evaluation, we found that deep learning models, especially LSTM, achieved the best accuracy while traditional models performed very lower. This shows that context-based models are more effective for Twitter sentiments analysis. Thank you. Now I am passing my floor to my mate.
Hello everyone, I'm Inathar Labib and I'll be providing a brief of the methodology that we followed in this project, focusing mainly on the dataset and its pre-processing. So firstly, let's talk about the dataset. For this study, we used a publicly available dataset from Kaggle. The dataset contains tweets that are manually labeled for both sentiment polarity and emotion categories. The sentiment labels include three classes: positive, negative, and neutral, while the emotion labels have distinct categories such as joy, anger, fear, sadness, and trust. In total, the dataset consists of several thousand tweets, making it suitable for our project. This dataset is particularly relevant for research because Twitter posts are short, highly contextual, and often noisy, which makes sentiment classification a challenging real world problem. Overall, this dataset provides a realistic benchmark for evaluating how well different models handle informal social media language, emotional expressions, and sentiment variability in real world communication. Now, here's an overview of the methodology. The main objective of this framework was to evaluate how model complexity and representation techniques influence sentiment and emotional classification performance on tweets. After loading the dataset and doing exploratory analysis, we focus on pre-processing the data. Then we implement and train multiple models, including a mix of classical machine learning models and deep learning models. Lastly, we evaluate the models with the same testing dataset for fair comparison. Now, let's dive a bit deeper into the steps of pre-processing the dataset. Pre-processing this data is an essential step before training the models, as tweets often contain informal language abbreviations, emojis, hashtags, and noisy texts. The primary goal of preprocessing in this project is to normalize the text while preserving meaningful, emotional, and contextual information. First, tokenization is applied to break tweets into smaller lexical units. Stop words were removed to eliminate non-informative words while retaining meaningful tokens. To differentiate punctuations and special characters such as at the rate or hashtags, we used regular expression. However, instead of removing hashtags completely, the hashtag keywords were preserved because they often represent emotionally meaningful or context specific information. Next, all texts were converted to lowercase to ensure uniformity and extra white spaces were removed. This step reduces redundancy and prevents different variations of the same word from being treated as separate tokens. So, by applying these processing techniques, we reduced noise in the dataset while retaining semantic and effective content, allowing the machine learning models and the deep learning models to focus on meaningful linguistic patterns on these tweets. That's it on my part. Thank you for listening.
So hello everyone. I'll talk about the model implementation part and also our key findings and observations. So to talk about model implementation, we have actually applied two kind of strategies here. First of all, we have applied traditional machine learning models and then we opted for deep learning models. For the traditional machine learning models, we use naive bias, logistic regressions, k nearest neighbor algorithm, random forest algorithms, and as we all know, these models actually rely on feature-based representations of text. So on the deep learning side, we implemented simple RNN, bidirectional RNN, and LSTM models. These models are especially suitable for text data because they can capture sequential and contextual information, which is missing in the feature-based representations as that is used in the traditional machine learning models. And as shown in the architecture diagrams, we can see RNN based models process text word by word, while LSTM improves upon RNN by addressing the vanishing gradient or exploding gradient problem, and thus allows it to learn long-term dependencies. And also uh, there are gates in the LSTM that actually control the important information and which should be carried from past to the present. And later on, we applied dropout regularization and early stopping strategies, which helped improve the generalizations on unseen data because we have to avoid overfitting. And due to overfitting, we all know that model performs well in training data, but when it comes to testing data, the model cannot predict well. So we have to always um, reduce overfitting in the models. Then moving on to the next slide, we are here to learn about key findings and observations. So we can see from the comparison chart, LSTM achieved the highest performance with an accuracy of approximately 75%, and thus it became the best performing model in our project. Simple RNN and our random forest are following LSTM, and they performed relatively well, but not as much as LSTM did. Overall, RNN-based deep learning models outperformed the traditional machine learning models. And why it happened, I already mentioned in the previous slide, because we know that um, for this kind of sentiment analysis task, it is important to hold context, but the naive bias, KNN, and others traditional machine learning language model, they don't rely on context-based embedding. They actually use feature-based representation of text, and that's why they perform not they don't perform that much well in when it comes to classify this kind of sentiment analysis task. Then to conclude, I'll say that our results clearly show that models capable of learning sequential and contextual dependencies, such as LSTM, are much more better suited for sentiment analysis than purely feature-based classifiers. And furthermore, deep learning models are more effective at capturing emotional nuances and contextual meaning, which are especially important when especially important informal text like tweets. So overall, I'll say this study confirms that LSTM-based approaches are highly effective for sentiment analysis tasks and can significantly outperform all traditional machine learning. Not all, also, because there is something called transformer, which is our limitation. We couldn't implement it. We welcome our um, next generation to come up with better techniques and strategies to improve accuracy of their models. So overall, I'll say that our LSTM-based approach have outperformed all most of the traditional machine learning models when it is properly trained and regularized. So that's it. If you are more interested to check out our project, you can see our dataset. You can also see our models, our data preprocessing techniques, our data analysis techniques from our .ipynb file. We have included it in the slide, and also our project report. So thank you for your patience.